Hi, I hope you're having as much fun as I am. This lesson is going to continue our discussion of what eigenvalues and eigenvectors tell us about systems of dynamical equations. And it will then also introduce something called staged population models coming out of Mooney Chapter 3. The note packet that I'm working through here is posted on Blackboard. If you want to print out and follow along, that's up to you. And there may be some page number overlap between a previous note packet that you had. If so, just discard the old pages and keep going with these. So let's look at this fox and rabbit population one more time, and then we probably better lay it to rest. I think the fox are getting a little tired of us spying on them. The fox in this population have learned, and we've seen from simulation, that if they eat too many rabbits, then everybody dies. The rabbits die, and therefore the fox starve. Suppose we have the same initial fox and rabbit population in thousands as we had before, and now the foxes decide to get smart and figure out how greedy they can be. So A in this difference equation is a measure of hunting effectiveness. So basically the rate at which the fox are eating the rabbits. The fox want that number to be as high as possible, but not to destroy the rabbits and therefore destroy themselves. Fox are smart. From the discussion last time, the fox know that the populations are going to be of this general form. F sub n is going to be some, say, b1 lambda 1 to the n plus b2 lambda 2 to the n, and the rabbit population is going to be some c1 lambda 1 to the n plus c2 lambda 2 to the n. Okay, we discovered this last time where we had a specific number for A, and therefore these constant coefficients B1, B2, C1, C2 were actual numbers that we could obtain. Lambda 1 and lambda 2 are the eigenvalues. And again, in the previous example, A was a specific number, and so we had specific numbers for the eigenvalues. This time, all of this information, all these variables, are going to depend on the constant A. But this is the functional form. And then the fox also know that the behavior of lambda to the n, if lambda is greater than 1 in magnitude, a term like this is going to explode, whereas if lambda is less than 1 in magnitude, it's going to decay to 0, indicating extinction. So all the fox really need to know are the eigenvalues. And so there are lots of maples in the woods where the fox lives, and so they go to maple, type in the matrix, or you could do it with the symbol palette entry form. And notice that I'm putting the variable A just right in here, and then I ask Maple to calculate the eigenvalues. So here is the matrix. Here are the eigenvalues, and they are given as depending on A, which, I mean, that's how it has to be, right? So here is, say, lambda 1. Here is lambda 2. And now the fox reason as follows. If either of these eigenvalues are greater than 1 in magnitude, then we'll get population growth. If they are both less than 1 in magnitude, then everybody's going to starve, and that critical value is when one of them is 1 in magnitude. So let's find that critical value where things sort of switch form between growth to decay. And it's going to depend on the larger eigenvalue. So the larger eigenvalue is, I look at these actually are going to be both positive numbers, I believe, and the larger of the two is with the plus sign. So 9/10 plus 1/10 square root 36 plus 50 times a. And what we're going to do is actually set this equal to 1. That's the minimal condition for stability here. So doing the algebra, subtract 9/10 from both sides, multiply both sides by 10, just writing down several key steps here. 36 plus 50a then should equal 1. If we square both sides and do some more math, minus 50a equals minus 35, and a turns out to be 7/10 or 0.7. And I think we actually saw this in a earlier simulation with Excel, very near the beginning of the course actually, before we got into the theory of this, that lambda equals 0.7 is sort of an important number here. It's the I'm sorry, a equals 0.7 is an important number here. It's the value of a that makes the largest eigenvalue equal to 1. So if lambda 1 is greater than 1, we get explosion. And if lambda 1 is less than 1, we should be talking about magnitudes here, we get extinction. And right at 1, we should get actually stability, at least in this case. And that tells the fox what they need to know. This is how hard they should hunt to make things go their way. Let's leave that example and the foxes to do their thing and go to another type of population model. Ecologists, biologists, people who study populations, especially who study populations with dynamical systems and other mathematics, know that just tracking the total population is not getting a handle on the whole story. Obviously, males and females have different roles in reproduction, and so quite often biologists only track the female population. And then focusing on that, for humans and many other mammals as well, females in different age categories play different roles in reproduction. First there's a maturation period, then a fertile period, and then a menopausal period where the female may still be alive but not capable of bearing offspring. And so for population growth, biologists track who's in each age category and then try to determine reproduction rates out of those individual categories. So here's a pretty simple case of that. Let's suppose we're going to divide the females into 3 groups, and you'll see this is a stage model in the sense that females are born into group 1, the youngest age, then they move to group 2, then they move to group 3, then they move out of group 3, then they're past reproduction capability, and so we no longer track them. They may have died, they may be still alive, but they're not interesting in terms of the population model anymore. Let's capture the information in this table in what's called a state transition diagram. So these are used in various areas of mathematics and computer science as well. There are 3 stages. And now we draw arrows for all possible transitions. Well, the natural aging takes everybody in category 1 and puts them in category 2. Those in 2 go to 3. But then we also draw births on this diagram. So for example, females in age category number 2 give birth to newborns which go into the youngest age category, And so we draw a transition arrow here like this. So then notice this arrow means the actual movement of individuals. This means the addition of new individuals. And mathematically, we can treat them more or less the same way, so we put them all on the same state diagram. Also, in the third category, females are giving birth to young who go in the first category. And in this particular case, you'll notice that the individuals in the youngest age category actually are reproductive mature as well. And so there's a loop. Individuals in age category 1 having young that go back into category 1. And now I can put the numbers from the table. So this information is saying from group 1 we give birth at 0.427 rate. So that gives the number that goes on this loop. And likewise for the other two birth rates. 8.498 and 0.1273. Actually, notice the relative sizes of these numbers. The individuals in category number 1 presumably are barely mature, and so they are reproducing, but not nearly at the rate that the more mature females are. And then by the time the females get to age category 3, they're less fertile than before, and so the birth rate is much smaller. Meanwhile, we can put on the other numbers in the table. These are survival rates. Over 99% of the people in age category 1 survive and move on to age category 2 in the next time step. Time steps might be years or decades, depending on the species or some other time interval. So like this and like this. So that's what number 1 was asking us to do, draw a transition diagram. This captures all of the necessary information, so now we can get the rest of the parts from here. So number 2 asks us to write the difference equations in both scalar and vector form. Let's write the scalar form, although I'll use vectors and matrices even to do that. So we're going to write a 3 by 1 equals a 3 by 3 times a 3 by 1. In this vector, I'm going to put the populations at the next time step, and there are 3 such populations, which I'll denote x1, x2, x3. And now notice that there is a notation conflict. We have been using x sub 1, x sub 2, x sub 3 to indicate the population at successive time steps. This is not time step, this is group number, but I also want to talk about time steps, so maybe now would be a good time to switch back to the function form like this. x1 of n plus 1, x2 of n plus 1, x3 of n plus 1. And I'm trying to write those in terms of x1 of n, x2 of n, x3 of n. So the net population at the next time stage in terms of the population at this time stage. And then if you remember how matrix multiplication works, that tells us how the numbers should go. So for example, xn is going to be multiplied by the entry in the first row and first column to produce part of the value for xn, x1 of n plus 1. That's the 0.4271. And likewise, the entry in the top row second column is going to get multiplied by the x2. That's the 8498. And the 0.1273. And when I multiply across this row down this column and add the products, that gives me exactly total contribution to xn plus 1. The population in the next time step in the youngest age category is simply the birth rates times the populations in the previous time step. For the second age category, there's only one way to get into the second stage, and that is to survive from the first stage. So the 0.9924 should go here. That's going to get multiplied by the x1, and then no contribution to stage 2 from previous stage 2 and 3 populations. And stage 3, the only way to get into that is to come from stage 2. So that is the 0.9826, and it goes in the second column and zeros elsewhere. That's the system in scalar form. If I write it in vector form, then I can just do my vector x of n plus 1 equals, let's call this matrix T, and then vector x of n. So these are the same thing with shorthand notation. If I go back to the matrix here, this is called the transition matrix. It tells me how to get to the next time step from the previous one. And notice the ordering here is important. Now that I've made my decision, this has to be associated with stage 1, 2, 3 in the columns and stage 1, 2, 3 in the rows. Furthermore, it's important to talk about where we're coming from and where we're going to. These are stage 1, 2, and 3, but they're telling us that we're coming from stage 1, stage 2, stage 3. And these are 1, 2, and 3, but they're telling us we're going to stage 1, 2, 3. So if I want to know something about from stage 1 to stage 2, that's this entry, from 1 to 2. So in addition, I need the information then that x1 at 0, x2 at 0, x3 at 0 are all 60. So initially the population starts out evenly distributed between the 3 age categories. Okay, that's what number 2 was asking us to do. Number 3 says, let's go ahead and use Excel. We could use Maple. Let's use Excel this time to calculate the populations in each age group over time. So we'll go to Excel. And here let's put the value of n, and here let's put population stage 1, 2, and 3. So n starts out at 0, and I don't think we'll have to take here. I don't think we'll have to take this model down very far. My touchpad's not working for some reason. Okay. Let's see if I can do it this way. Maybe that'll be enough. And let's enter formulas. Well, first of all, the initial age distribution are 60s. And then here. So now I want to know what's happening to the first, the population of the first stage in the next year. So now I'm basically reading off this row times this column, and these are the previous year's stage populations. So equals my 0.4271 times the previous stage 1 population plus 0.8498 times previous year stage 2 population plus 0.1273 times previous year stage 3 population. And similarly, formulas for stage 2 as a function of the next. This one's easier. It's just 0.9924 times x1. Times this one. And the third one, I get the 0.9826 times previous year's population in stage 2. Okay, and let's take these and drag them down. Good for population 1. I'm double checking with my previous results just to make sure that I've typed things in. Okay, that looks alright. So what you see here is growth in all 3 stages. In fact, you might be also interested in the total population, and so let's make a column for that as well, and in any given year add the total contributions from the stages. So what we clearly see is growth in the total populations, and not dominated by any one of the stages. Those stage populations are all growing as well. If we think back now, we haven't calculated the eigenvalues of the state transition matrix, but I'm pretty sure that at least one of them is greater than 1 in magnitude in order to give this population growth. We can actually get more precise here. So maybe I'm not only interested in knowing what the total populations are doing, but how the age distribution is coming. Like, is the percentage of the total population that's in stage 2 constant over time, or is that growing or declining? So that could have long-term implications. If my population overall is aging, for example, then at some point maybe my model will become invalid, and the population would probably decline under that scenario. So let's make population 1 percent, and likewise for the other categories. And what I'll do here is pick up the population in stage 1 and divide it by the total population for that year. And let's see, I think I can go ahead and, no, I might not be able to just drag right. So second is here divided by here, and third is here divided by here. And now I think I can highlight these and drag down. All right, now we see something more interesting happening. The total populations in each age category are growing. The percentages, obviously, or proportions, can't grow. They have to add to 1 at any given time stage. but you see stabilization. So as we go down these particular columns, the numbers are approaching fixed proportions. By the time we get here to 10 time steps, it looks like in the long run about 40% of the population is going to be in stage 1, 33% in stage 2, 27% say in stage 3. Let's see if we can predict that information from the theory. So on the next page of the notes, actually, I have done just what I did in this spreadsheet and generated these numbers. I also went ahead and generated a graph of the proportions. Just for emphasis to show that clearly, though the populations are growing, the age distribution proportions are stabilizing. If we did go to Maple and enter our transition matrix, here's how you can do it with the matrix command. You could more easily do it with a symbol palette, and ask for the eigenvalues and eigenvectors. Here they are. Again, this is lambda 1, lambda 2, lambda 3, just for purposes of discussion. Comments about several things. First of all, your version of Maple may give these same eigenvalues, but in different order. There's no reason why we have to call one of them, any particular one of them, lambda 1 versus lambda 2 versus lambda 3. So it's okay to have the different order of eigenvalues, but then Maple should also, in the eigenvector matrix, be giving you the corresponding orders. Second comment, it's like, what is this business? Here's a number plus 0, I. So capital I is Maple's notation for the imaginary unit, square root of -1. And in each case, the coefficient on the I is 0. So, though we won't go into this much, eigenvalues certainly can turn out to be complex valued. In this case, Maple is prepared to give complex values, but these happen to work out to be real valued. So I can ignore this part for purposes of this example. Then I come back here and say, what about a dominant eigenvalue? In terms of magnitude, it's clearly the first one. So this is the dominant eigenvalue, largest in magnitude. And indeed, it is greater than 1. That's why we're getting population growth, as we saw, as opposed to extinction or overall population stability. Okay, if this is the dominant eigenvalue, then we can come here to the first column, because lambda 1, for my example, is the dominant eigenvalue, so P1 then is going to be the associated dominant eigenvector. I'm ignoring the complex parts. And let's look at this more closely. Remember that when we have an eigenvector, we can always multiply it by any constant and get another eigenvector. So what I'm going to do here is normalize this eigenvector to have total sum 1. Right now it has total sum, just to take a few significant digits like this. .7092, and so to normalize, that would be to take the 6871, divide by 1.7092. Likewise, to take the 0.5639 divided by 1.7092, and finally the 0.4582 divided by 1.7092. And let's compute each of those. and you get 0.4020, 0.3299, and 0.2681. So I could have just as easily replaced these three numbers with these three numbers, which have the advantage of adding up to 1. And those should look familiar. Where have we seen 0.402, 0.329, 0.268? It's here. So here's the upshot of all of this. In a situation like this, where I clearly have one dominant eigenvalue and the others decay, over time I can ignore everything except the first eigenvector. And then the neat thing is that if I normalize the first eigenvector, its components actually tell me the proportions of the individuals in each of the three age categories. In other words, this problem is completely solved. By knowing the eigenvalues and eigenvectors, I don't have to do simulation at all. I can tell you exactly what is going to happen, whether there's going to be explosion or extinction, and if there's explosion, I can tell you the relative proportions in the age categories just by looking at the appropriate eigenvector. This problem, again, is completely solved. Notice that it is a linear equation. X appears to the first power, vector x appears to the first power, so to speak, in this equation. Later on, we will study nonlinear equations. That's a different matter altogether. And I'll stop here. Thank you.